In this lecture, we are going to introduce neural networks. More precisely, we are going to study fully connected neural networks, the simplest form of modern neural networks. In supervised learning with scikit-learn, you have seen some classifiers like K and N. There are many other classifiers, some of which are very good, like random forest, Adaboost, or support vector machines. These classifiers work well when the data is given on vectorial format, as features. However, most of the data is not given as features. Instead, the data is in some rich format like images, speech, text, or video. In those cases, what people did before was to use another algorithm to extract those features. In computer vision, the majority of last decade's research was on finding algorithms which get good features from images. Perhaps the most famous of those algorithms was the SIFT algorithm, which given an image returns features from that image. Then those features are classified using a classifier like SVM. Maybe you can see the problem here. In order to solve the problem, we are optimizing two different algorithms, SIFT and SVM, which aren't related at all with each other. Neural networks work a bit differently. They have an input layer, in the figure denoted with 1 or more hidden layers, denoted with 2, and an output layer, denoted with 3. The job of the hidden layers is to get good features, while the job of the output layer is to classify those features. With the net being trained end-to-end, we have a single algorithm which at the same time both finds good features and classifies them. This has shown to work very well, and so neural networks have revolutionized many fields, to the point of making the old algorithms obsolete. Let's have a closer look at the network given here. Each neuron, or better called unit to avoid analogy with biological neurons, in a layer is connected with every unit in both the previous and the following layers. These connections are called weights and are represented by a matrix, or tensor. As input, we have input layer containing 10 units. In order to get the values of the first hidden layer, H1, we multiply the vector of features with the first matrix of weights, called W1. Look at the matrix of weights. The first dimension should always correspond to the preceding layer, while the second dimension to the following layer. As you can imagine, H1 contains 20 units. Similarly, we continue for the second hidden layer, H2, which is a product of the first hidden layer, H1, and the second matrix of weights, W2. Finally, we get the results of the output layer, which has 4 classes, by multiplying the second hidden layer, H2, with the third matrix of weights, W3. Writing neural networks this way is a bit complicated. Fortunately, PyTorch has a better way of doing it, which is object-oriented. We define a class, let's call it net, which inherits from nn.module. Look that we are importing torch.nn. In the init method, we define our parameters, the tensors of weights. For fully connected layers, they are called nn.linear. The first parameter is the number of units of the current layer, while the second parameter is the number of units in the next layer. In the forward method, we apply all those weights to our input. Finally, we instantiate our module by calling class net, and we get the result by applying object net over our input layer. Let's practice building some neural